Good afternoon. Today we will learn more tricks about writing shellcode. Regarding the assignment submission, I extended the due date for the shellcode challenges until Thursday. So all week 3 challenges are due on this Thursday. So please take some more time to write your shellcode. And when you submit the write-up, please don't forget to include your short shellcode and description about how you get the shell out of the program execution in the write-up, because I will check your write-up to give the extra credit score for the shellcode that is shorter than 12 bytes. And another thing to note is that the due date for alphanumeric shellcode 32 and the Stack Overflow Where 2, the 2 extra credit challenges, are at the end of this term. So you don't have to finish that in this week. But please challenge to solve them because the extra credit points are quite high and it's very fun. And then for the next, I will go over some tricks that you can apply for writing short, ASCII, or alphanumeric shellcode. First, check the following for the moving an immediate value to a register. I have listed 3 ways to move 0xb to EAX. The first instruction is the direct moving the value 0xb directly to EAX. But we cannot use this instruction because it contains a 0, because moving a value to EAX directly only 1 byte, even only 1 byte, because the byte width the register width is 4 bytes, so it will automatically add the 3 0 byte to this 1 byte value. So we cannot use this in non-zero shellcode, but in this case we can use a 1 byte move instruction. But the restriction is that the target register must be the 1 byte register of EAX, which is AL. And in this case, we can reduce the length of the opcode to 2 bytes, B0 and the target value 0B. But because this only changes the AL part, the lower 1 byte of the EAX register, we first need to make all high bits of EAX as 0, or simply making EAX as 0 to use this instruction to set the value of the EAX as this value. And the reason why I choose the value 0xb is because it's a system call number for execve in 32-bit machine, and we need that to execute some program at the end of our shellcode. And lastly, the way that I recommend you to use is push a value, 1 byte value, and pop a register. These instructions, 2 instructions, the first instruction can push any value, so it's universal. So you can put any kind of the 1 byte value, if it is a positive value, to the stack, and then pop EAX. Then it will set the entire 4 byte of the EAX register as 0B, 0000000, and then 0B. Yeah. So you can just consume like a 3 byte opcode, and you can set any kind of bytes to the entire EAX register. And another good thing is that the 6A and 5.8, these are alphanumeric character. So if your target value is alphanumeric, for example, 30, 31, 32, this kind of the number, then like the entire opcode, 3 byte opcodes will be alphanumeric. And next is moving a register value to another register in 32-bit machine. We can directly use the move instruction. For example, if you want to move the value of the ESP to EBX, which we use for setting the first argument of the execve, the resulting opcode is 89E3. But these values are non-ASCII. A9 is non-ASCII at all, A3 is non-ASCII at all, and the non-ASCII means that these are non-alphanumeric. So in that case, we cannot use this move instruction even in the ASCII and also for the alphanumeric shellcode. And another way to do that is we can use stack as a temporary storage and use that to move past the value to the register. So one way to do that is like a push ESP and PopEBX. So the effect will be equivalent to like just moving the value of ESP to EBX, but check out the opcodes. So 5.4, 5B, these are ASCII values. And the PopEBX is not alphanumeric, but if you want to move the value of ESP to ECX or other register other than EBX, then these are alphanumeric. For example, if your target register for POP is ECX, then it's a 5.4, 5.9, which is character T and Y in the capital letters. So you can move register values in alphanumeric by using push and pop. And the same trick may be used for reducing 1 byte opcode in 64-bit. Check out this instruction, moving the value of RSP to RDI. It requires 3-byte opcode. But if you do push RSP, pop RDI to set the first argument, it only requires 2 bytes. So you can reduce 1 byte opcode in writing short shellcode in 64-bit. So please use this kind of trick to reduce some more bytes in your shellcode. And in 32-bit example, I just told you that you can't use a PopEBX in alphanumeric shellcode because the opcode of PopEBX is 5B, which is the left squared bracket this character, and this character is not alphanumeric, while all the other 5 these push and pops are alphanumeric. However, you need to set the value of EBX because that's the first argument of the exact VE, the program path. You need to set that. Then, how can you do that? And I would recommend to use PopA. Then, what is the PopA register? If you do a little search, you may find the link below, and reading that will tell you that it will pop all the registers from the stack in a sequence of EDI, ESI, EBP, EBX, EDX, ECX, and EAX. No, this is not a sequence. The correct sequence is this one. Yeah. All right, yeah, EDI, ESI, EBP, and then it will ignore popping up the ESP because like doing that will change the stack, so it will affect on the popping all these 4 register. So like it will just skipping the popping the ESP, and then pop EBX, EDX, ECX, and EAX. And to use that, we need to push register values beforehand because it's a popping all registers. And think about the push is an inverse operation of pop. So we just learned about the popping order as EDI, ESI, EBP, ESP, EBX, EDS, ECX, EAX from this pseudocode. Then the push order should be the reverse of the pop order. Knowing this, let's set all the register value except ESP because the PopA instruction ignores the changing of the value for ESP to specific values such as EAX is 31, EBX is 32, 33, 34, 35, 36, 37 in hexadecimal. Yeah. And to do that, we push all the values in the stack with the push order. So we first push EAX, ECX, EDX, EBX, and ESP ignored. So we push any kind of the alphanumeric character here to make the entire thing as alphanumeric, and EBP, ESI, and EDI, and PopA. And if you do make 32 and make print, then you will see that all the instructions, the push immediate value is, the opcode for that is J, and the immediate value, all the immediate value here are alphanumeric. And also the PopA, that instruction is a character, small character A, lowercase character A, so the resulting shellcode, resulting opcodes are all alphanumeric. And let's check if that changes the value of the register correctly. So to do that, you can attach GDB to /shellcode and break it main and run it. Then it will push all the values. And if you reach the execution to the PopA, this is the register status before running this PopA instruction. And after running that, it will pop all the register value except for ESP and setting the value accordingly. You can check all these values set as like how we push the values in the stack. So the implication is that you cannot use a PopEBX in writing alphanumeric shellcode because that opcode is not alphanumeric, but PopA is alphanumeric, so you can use that to change the value of EBX as well as the value of other registers except for ESP. Because this is an alphanumeric instruction, the PopA itself, so use that in writing alphanumeric shellcode. Next is about reducing some more bytes for creating 0, which is required for second and third argument for execve and marking the end of the string or something like that. And in writing shellcode, at the end, we must set EAX to the value of the sys execve at some point, because at the end, we need to execute execve system call in our purpose of writing the shellcode. And that value, that system call number in 32-bit is 0xb. And to do that, try to do the following, as follows. So for example, push 0xb, pop EAX, and this will set EAX as a 0xb. And then running this instruction, CLTD, which is opcode 99, just 1 byte, will set EDX as a 0. So you can create the 0 byte, the register value as a 0 by using just a 1 byte opcode. And then why this instruction sets EDX as a 0? You can find information about this CLTD, and its alias is a CDQ, this instruction from the link below. And briefly, what it does is that it will represent a 64-bit integer in 32-bit machine by using 2 registers as a 1 integer. And then the 32-bit Intel CPU will use EDX for the representing the high bits of that 64-bit integer, and EAX register as the lower 32-bit of that integer. But it will extend the value in EAX as a 64-bit, and in doing that, it will do sign extension. And that means if EAX stores a negative value, it will set the entire value as a negative. And then if EAX stores a non-negative value, then it will regard the entire value as a non-negative value. And in doing that, interesting thing is that how Intel CPU represent negative value is using 2's complement, and the negative value start with the sign bit, which is the top bit of the integer as a 1, and then that representation requires if EAX stores a negative value, then running CLTD will result in setting the EDX value as a all 1, because that will represent the negative value of the same negative value that EAX points in 32-bit. but the EAX stores a positive value or non-negative value, then EDX will be set as 0 by running a CLTD instruction. So if we run these three instructions, push 0xb, pop EAX, then the value of the EAX will be positive. Then running CLTD will do sign extension, then it will store EDX as 0. So you can create you can make a register, a EDX register, to have a 0 as a value by just spending one opcode. And this will be helpful for writing a short shellcode. And next is about reducing more opcodes and also reduce the complexity of the ASCII and alphanumeric shellcode by reducing the privilege escalation step in your shellcode. We've learned that the your shellcode is required to run 3 system calls, which is a get EGID, set regid, and execve. But you can remove the call to get EGID if you know the exact effective GID value for the escalation. So in this case, you can directly, if you know the exact GID value, so if you know the expected return value of this system call, then you can put that value directly in your shellcode. And to check that target group ID, you can refer to the etc password this file, and then if you run this command, it will print out all the UID and GID of the challenge. So for example, if you want to escalate the privilege in the alphanumeric shellcode 32 challenge, then your target GID must be 30,000. And then for ASCII shellcode 64, your target GID is 30,001. Yeah. So you can remove the call to get EGID and then just directly put this GID value. But you don't even need to do that. So you can go further to remove the requirement for running set regid. And the reason why you need to run set regid is that the shell program binsh does not automatically inherit the privilege. So we need to run the set regid before executing binsh, the shell program. But that does not have to be in your shellcode. The only requirement is that you need to run that before running binsh. So one of the tricks is that you can create a binary programs that runs the following code. So just writing a main function and run set regid, get EGID, and then run binsh, and compile this program, and in your shellcode, without calling this system call, just do execve and running this program. So the program execution will be your shellcode will run this program, and this program will do this get EGID and set regid, and then run binsh. Then it will inherit the privilege first, and then run binsh next. So all requirement fulfilled. So this will be very helpful for reducing additional steps for calling system call and alphanumeric shellcode. So you only need to call int 0x80, which is CD80 in alphanumeric shellcode, by just one time. And another way to reduce more bytes in short shellcode is to reuse some existing values in the register and stack. One thing that you can try is reusing some existing string value for file name. For example, in short shellcode 32, if you break at the point of the starting to running the shellcode, then you can see that the ESI points to 804B410, and that stores the summed value. And if you printed that value, then this will be FVAD240C. And if you print that as some of the byte sequence, then 0C, 24, AD, FV, and it ends with 0, which is end of the string. So you can regard address of the address pointed by ESI stores a string 0C24ADFB because 4 byte and end of the string. So you can reuse this as a file name. So push ESI PopEBX, then the EBX will store the address of this string. And then if you create a symlink that the program A to this as a file name, then you can use this EBX value for your execVE system call. And I just teach you like you can reduce the additional system calls such as get EGID or set EGID by running this program. So if you create this program as a binary A, then you can get the shell by supplying EBX as this value to your execVE system call. Finally, about writing self-modifying code for alphanumeric shellcode. If you can set the value of the EDX as the address of your shellcode, the starting point of your shellcode, then the following instruction, XOR CL to 42 over EDX, will apply this kind of the operation. So what this instruction will do is like if we set the EDX as the address of the shellcode, then it will change the byte at offset 0x42 of the shellcode by applying XOR to the value in the CL. But if you set it as like a full 4 byte or something, then it will apply like an XOR to ECX, then store it back to the shellcode. So this fulfills a self-modifying code. And this is required because we need to run the interrupt to 0x80, which is its opcode is CD80, and both of them are non-ASCII, non-alphanumeric character. And because we can only use alphanumeric character in our alphanumeric shellcode, so we need to create that. Then suppose your shellcode at offset 0x42 stores the value 0x32, which is number 2 as a character, which is alphanumeric. And suppose the register value of the ECX stores a -1, which is a 0xFF as a 1 byte. Then if we apply this kind of the XOR, then the resulting value will be CD, which is the opcode for interrupt. So we can create 0xCD from the alphanumeric value by setting the EDX as the starting of your shellcode and using this instruction. Then the challenge is that how can we set the EDX as the address of the shellcode? We can get the address of the shellcode from GDB. So for example, I just wrote this shellcode and then running the alphanumeric shellcode 32 with GDB, get to the point of the execution of the shellcode and get into there, then we can know that now the EIP is at this address and across multiple runs, it'll be at the fixed address. So now you know the shellcode is at F7FD2000. Then it's also problematic because how can you put this address value to EDX? So this is not an alphanumeric value at all, so we cannot push and pop or something like that. So if we directly push these values, then F7FD and then even 00 will be rejected from the alphanumeric shellcode. Then let's creatively think about like how the program runs this shellcode. And if you check the instruction to run the shellcode carefully, then what it does is that it will call the address on the stack, EBP minus 0xC, which is a local variable. And we know that the local variable is in the stack, then maybe we can find this address from the stack. So let's do that. And if you print out 0x x to just 2 values from ESP. Maybe you can print further values if you can find it, but by just printing 2 values, you can see that the first value is this one, and then the second value is F7FD2000, which is the address of the shellcode. So the target value, this one, is at the ESP plus 4. So to set the shellcode address in this alphanumeric shellcode 32 challenge to EDX, then what you need to do is a PopEDX for popping this value to EDX, and then PopEDX again. Then you can set the address of the shellcode as a value of the EDX. And note that the PopEDX is definitely an alphanumeric instruction, so you can use that. So by combining all the skills, such as PopA for changing all the register values, and also PopEDX and setting the value of the EDX as a shellcode address and applying XOR, then you can create the self-modifying alphanumeric shellcode. So please don't give up and please try it because it's quite fun. But I know your time budget is quite tight, so please do not push too hard for that. Yeah. And this is the end of the material for today. And please have fun and enjoy writing shellcode. And we will move to the week 4, starting on this Thursday. Thank you.